Hi all, welcome again to another video. In today's lesson I'll be introducing you to the concept of linear elasticity, and we will discuss the stress strain behavior of the body under a tension load. So let's begin. Remember, the prime application of any structure is to carry load. In the previous videos we have discussed one important parameter called moment of inertia. Moment of inertia is dependent on the cross section. The more moment of inertia, the better its load carrying capacity. The next important parameter is a material dependent parameter, and it's called as Young's modulus. Let's see what is Young's modulus in the next section. To understand the concept of Young's modulus, we need to learn about tensile test. In a tensile test, a test specimen is stretched along its length until it fails. During the tensile test, when the load keeps on increasing, before the specimen fails, it would continue to stretch and deform. This deformation can be clearly seen with the naked eye and looks somewhat like this. This behavior of the specimen to permanently deform through reduction in its diameter or thickness is called as necking. When you keep on applying load even further after the permanent deformation is observed, you might see after a certain limit the specimen failing completely. Once the specimen fails, the tensile test is completed. Oh, I forgot to mention that there is an intermediate step before the necking occurs. This is rather the very first step that happens once applying the load. In this stage, the particles in the specimen will start to displace, but no visible change will be seen. So at this stage of the test, the specimen would look something like this. There will be some changes in the length of the specimen in the direction of the applied load, but perpendicular to the direction of the load, there will be no change in the dimensions. At this stage, if the load is released, the specimen will regain its original length, meaning whatever the stretch experienced by the specimen will vanish once the load is removed. This phenomenon is called as elastic behavior of the material. Now in the next section we will discuss this behavior more in detail. Okay, so let's try to understand what happens within the specimen when there is elastic deformation. As we saw earlier, the particle inside the specimen will move along the direction of the applied load. This movement will induce a deformation in the specimen. Now if you remember, when we discussed the moment of inertia, we defined moment of inertia as the resistance provided by the virtue of the cross section of the structure to the deformation. Similarly, the material of the specimen itself will induce some resistance to the applied force. This resistance is called as stress, and usually it is represented with Greek letter sigma. We can quantify the stress developed within the specimen as the ratio of the applied force to its cross section area. There is one more terminology to learn, and that is strain. Strain is simply the deformation due to the displacement of the particle due to the applied load. Strain is denoted by epsilon and can be quantified as the ratio of change in length of the specimen to its original length. Monitoring the stress and strain in the specimen during the tensile test will be very helpful in understanding the material behavior under load. In fact, by plotting the stress against the strain, we can derive many important material parameters. For this lesson, let's see whether we can extract Young's modulus from the stress-strain relation. Okay, so on the left hand side we have a representation of tensile stress starting from elastic deformation, then necking, and finally the failure. On the right hand side we have an empty plot to draw the stress-strain behavior of the specimen during the test. On the x-axis we have the independent parameter epsilon, which is the strain, and on the y-axis we have the stress, which is sigma. During the elastic deformation, we can observe that when the strain in the specimen increases, the stress increases linearly with it. Then when the necking starts to occur, we can see that the linear behavior changes into nonlinear. As the permanent deformation occurs, we can see that the stress-strain curve increases for a while, and after a certain level of strain, the stress developed within the specimen starts to drop. And finally, when the specimen fails, you can see the stress-strain curve breaks, marking that there is no load on the specimen and thereby no stress as well. Now let's concentrate on this linear stress-strain behavior. This occurs when there is an elastic deformation in the specimen. This linear stress-strain material behavior is also called as the linear elasticity or linear elastic material model. To define this linear elastic behavior mathematically, we can simply calculate the gradient or the slope of the stress-strain curve. This will also give us the Young's modulus. So, as a definition, Young's modulus is the slope of the linear elastic stress-strain curve. It is denoted with the letter E. Young's modulus is a very important material parameter. The load-bearing structure often experience elastic strains than the permanent plastic strains. So, as long as the structure experiences load in its elastic deformation region, it is very unlikely to fail. To perform calculations on the structures in the elastic region, Young's modulus as a material parameter is inevitable. So that's it for this video. I hope it was useful to understand the concept of linear elasticity and Young's modulus. In further videos, we'll be discussing a lot more concepts in engineering mechanics, so like and subscribe for more content. Thank you for watching the video. Bye bye.